All right, now let's get into the actual nomenclature of coordination compounds. And I mentioned this in passing as we were talking, the idea that we have a central metal, in this case silver, and we have some number of ligands around it. And this is can be an organic group, it could be an anion that's attached to the metal center. And finally, we end up here with a complex cation. And so what's going on here is we have an empty orbital on the metal center. We have a filled orbital, in this case the one for the lone pair on ammonia, and that empty pair of that pair of electrons donates into the empty orbital on the metal. We'll talk about two types of ligands. So we have monodentate ligand. Here is two ammonia molecules, and each one of these lone pairs could donate to a metal center. If we took the power of organic chemistry and we did away with two of the hydrogens and we used a CH2CH2 linker here, we would end up with a really common ligand called ethylene diamine. And all we've done now is take and chain ligand 1 and ligand 2 together into a chelating or a polydentate ligand. So two monodentate ligands, so this can bind to one metal, this can bind to one metal. This ligand can bind to the metal using this lone pair and can bind to the metal using the other lone pair. So this often will occupy two sites on your metal center. Here's a few common ligands: water, ammonia, chloride, cyanide, carbon monoxide, thiocyanate, and hydroxide. Cyanide basically always binds through the carbon. Carbon monoxide does the same. They've highlighted both ends of the thiocyanate because depending on the complex, actually it can donate through the nitrogen or through the sulfur. And then here's a few common bidentate ligands: ethylene diamine, which we saw on the previous slide, which has two nitrogens. Glycine, which is a amino acid, can act as a ligand, donating a pair of electrons from the nitrogen and donating a pair of electrons from the oxygen. And then oxalate is a very common transition metal ligand. It can donate a pair of electrons from this oxygen, a pair of electrons from this oxygen to a metal center. So chelating ligands. Here is the cobalt center with 6 ammonias around it. Well, using the power of organic chemistry again, we can link each pair of these together, and with the ethylene diamine ligand, then we have this complex instead. So rather than having 6 ammonias, this has 3 ethylene diamines, with each ethylene diamine having 2 lone pairs of electrons that it can donate in. Ligands are very common in biological chemistry. The porphyrin ligand is a part of the heme, which binds oxygen in our body and the body of other organisms. The iron center is ligated by 4 nitrogens. This porphyrin ring acts as a tetradentate ligand, supplying 4 lone pairs to the iron center. We have a imidazole ligand here at the bottom, supplying a lone pair to the iron, and then finally the O2, when it binds, is acting as a monodentate ligand to the heme center. All right, we need to dissect these complexes a little bit, because in order to do naming, we need to figure out what the charge is on the metal, and that often will require a little work on our part. Here, I've actually only given us the complex cation, and so we have to figure out what charge would need to be on the metal in order for this 2+ charge to be the charge on the complex cation. NH3 is a neutral molecule. There's 4 of those, so 4 times 0. There's no charge at all from the ligands in this case, and so all of the charge, the entire 2+, comes from the metal center. And we'll always work them out in this way. Knowing the total charge and the charge on each ligand, one can determine the oxidation state of the metal always. And so ammonia is a neutral molecule, and it still is. Chloride is neutral, chloride has a -1 charge. Each nitrate has a -1, so -1 for chloride, -1 for nitrate, -1 for the other nitrate. There's 3 minus, and the entire thing is neutral, and so this has to be a rhodium-3 that we have here. Okay, so X plus 5 times 0 for this ligand, plus 1 times -1 for the chloride, plus 2 times -1 for the nitrates must be equal to 0, and so the charge on the rhodium has to be 3 plus, so that this whole thing is neutral. 3 plus 0 -1 -2 gives us 0 overall. Another way to dissect this would be, and sometimes it makes sense to do this and sometimes it doesn't, either way it will work out to give you the same charge, is to first pull the complex cation and the simple anions apart. And so if I simply pull off the 2 nitrates, I get this complex cation which has a 2 plus charge, and then my 2 nitrates, and it has to work out to be the same, and so whatever the charge on the metal is, plus 0, -1 must be 2 plus, and so 3 plus -1 gives me 2 plus, so it has to be a 3 plus charge that's on the rhodium center. All right, one more example, and like I said, we could do this either way. So I have a complex, I have a chromium with some oxidation state, I have 4 neutral waters, I have 2 chlorides that are ligands and 1 chloride that's not a ligand. So I get 3 minus from the chlorides, so this must be chromium-3. 3 plus 4 times 0 plus 2 times -1 plus the -1 must be 0. And again, we could approach it the other way. We could pull off the chloride, and this would give us a +1 charge on our complex cation, and then this must be 3 plus, so that 3 plus -2 gives me 1 plus. All right, one final one. So in this case, cyanide, the cyanides each have a -1. It's Cn minus for each one of these. And so 4 minus. And potassium is in the first column. Each one of these has a +1 charge. So +4 from the potassiums, -4 from the cyanides means that this has to be a 0 charge from the nickel. Okay, so the ligands each have a -1 charge. These cations each have a +1 charge, and so there's no charge required on the nickel for the whole complex to be neutral.